everyone. So in the last session, we have discussed on counters and also have shared the counters assignment. Have you tried with the counters assignment? Counting multiples of 5, multiples of 3, skip multiples of 5, and up counting, down counting. Any doubts in that, everyone? What about Vinita, Sunny, Sumalata, Rakshita, Lahari, and Sai? And have you completed all Verilog recorded sessions? Sunny and Sai, Rakshita?
Yeah, yes, ma'am.
How many
Ma'am,
assignments completed till now?
Ma'am, I have completed first assignment in my old laptop,
Okay.
and I have in my new laptop I can't able to install the Quartus Prime, ma'am.
Why?
I don't know. I want to ask in shop tomorrow, ma'am. Yesterday shop
Okay.
was leave. Today some work is doing, and tomorrow I will check it, ma'am.
Okay. Okay. Fine.
Okay, ma'am. Mm.
And how many sessions left? Recorded sessions?
I
Rakshita?
think I have completed 10 sessions, ma'am.
Okay. All topics clear till registers counters?
Ma'am, I'm clear, but if once I tried all thing, I will. If I have doubt, I will ask you, ma'am.
Sure. What about
Okay, ma'am.
Sunny?
ma'am, I completed till 7 and I'm working on assignment on flip-flop assignment.
Okay, fine. So, any doubts till now? Are you able to write the program properly without any errors?
Yes, I write. I write. I can write.
Okay, sure. What about Sai? You
Ma'am, I
need to submit
completed.
the,
Hello.
yeah.
Yeah, I completed all the sessions, ma'am. Presently, I'm working on the flip-flop assignments. Verilog flip-flop assignment.
Okay. So how you are doing assignments? Are you doing in your tools or EDA playground?
I'm doing an EDA playground.
Okay, I told you everyone to attach the EDA playground links in the Excel sheet in assignment 1, assignment 2, 3, like that. Are you doing that same? I didn't receive any Excel sheet from anyone till now regarding assignments, coding assignments.
I will attach it, ma'am.
Okay, try to do that in future. It will be helpful for you also. Okay, it is easy to refer all the assignments in one Excel sheet from Verilog system, Verilog UVM project protocol. So everything will be in one page. Okay. So what about Lahari?
Ma'am, working on flip-flop assignment
Okay.
and need to attach the coding in the Excel
Okay.
for the first assignment.
Okay. So did anyone try counters assignment? Counters not yet started. Sumlata, Vinita.
No, Prasanti.
Okay. Fine.
I've completed only one assignment. I'll share it to you.
Okay. And also yesterday I have shared some books in the SharePoint drive for digital logic design interview question preparation and also Verilog HDL interview preparation questions, books for reference and also some assignments. Okay, whenever you get the time, you can just go through those ones. Okay, whenever you are getting some free time in weekends. Okay, So clear, everyone? Today we are going to discuss on few important concepts in Verilog. Okay, till now we have completed all major concepts of Verilog, and also in the last session I have given some assignment for you, how to do the swapping operation using a blocking and non-blocking assignment, and what is the difference between intra-assignment statement and inter-assignment statements, regular delays and inertial delays. Everyone gone through these things? Did everyone gone through these things? Sumalata, your voice is
Yeah.
not up.
Okay. And now are you
Okay.
able
So,
to?
yeah. What is the difference you have observed between intra-assignment delay and inter-assignment delay?
Actually, I worked on that assignment by using assignment operator. Swapping I have done. I shared in the Excel sheet also.
Okay.
Yeah, but particularly I didn't to notice that delays. I will check today.
Okay, fine. So just try from your side. Anyway, in verification concepts, I will explain you all type of delays in Verilog. Okay. Mostly today we will cover three major concepts in Verilog. One is inferring of bad latches and how we can do a for loop synthesizable. Actually, for loop or for each, forever, repeat, initial, all these blocks are non-synthesizable. That means we can use only in the test benches. We cannot use in the synthesis. They never generate any circuit netlist. Okay. But how we can make for loop as a synthesizable, where we can generate some circuit netlist for loop. Okay, that's what we are going to see today. And also UDP concept, user defined primitive, that is not much important. We never use that concept in real time. It's a very old version, but we will just discuss how we are going to write the program in UDP, how the programming format. So we need to know, right, every concept properly. So for that purpose, we will discuss UDP concept today. Okay, so all these three concepts will be completed. These all are just minor concepts. Okay, and in Verilog till now we have completed all major concepts. If you see from starting onwards, data types, operators, procedural assignment statements, continuous assignment statements, like our rules we already discussed, and what are the different loops, like always, initial, case statements we didn't discuss, right? Case we will discuss one day. Case X, case Z, parallel case, full case. These things we need to discuss. And also we discussed loops, all loops, like a repeat block or forever, for each, initial, always, everything we have discussed. And also till now we have designed the combinational logic circuits, structural modeling, behavioral modeling, data flow, everything. And flip-flops we have designed, registers, counters also designed. Okay, so these are what blocking and non-blocking assignments also we have completed. Begin and sequential execution statements, fork join, parallel execution statements. Okay, all these things we have completed, and how we can generate the clock by using always, block, repeat, forever, different ways of generating a clock. All these things are completed. Okay, mostly 70% of Verilog completed. Okay, and the leftover topics are today topics and verification, test bench concepts, final modeling of finite state machines, memories. Um, those are like a bit high level. Finite state missions and memories we will discuss very clearly, because those are like a project based. If you know how to write a single finite state mission, just a simple example, you can able to design any type of project in FSM, because in future whatever the protocols we are designing, like UART protocol, I2C, APB, AHB, AXI, and any project, whatever the project you are taking, most of the project and protocols, we use the finite state missions only. Okay, because you already know what is meant by finite state machine. It is a complex sequential logic circuit where we can write every functionality in terms of states. Okay, total functionality we will divide into the number of states. So based on number of states, we do some task. So that is a easy implementation in digital electronics, and also for writing the program, it is very easy. So whatever in future, like digital clock or traffic light controller or vending machine or any type of project, minor project, mostly we will implement with the finite state machine only. So FSM memories are most important concept. In memories also we will discuss RAM, how to design RAM memory, ROM memory, FIFO, first in, first out, FIFO memory, these things. Okay, mostly by next week we will complete. Wednesday there will be no session. We have a festival, right? Shivaratri. So Wednesday there will be no session. So this week mostly next another session will be there. If possible, I can take on Sunday. Okay, instead of Wednesday. And mostly next week we will complete a Verilog syllabus. Okay. So, but from your side also, don't put any pending works. Okay. So if you don't have any pending works, then it is easy to continue with the system Verilog, because from March 1st onwards, we are going to start a system Verilog. Okay, from March 1st onwards. So still 4 sessions, 4 days left. March 1st this week or next week? Let me check.
Week, ma'am.
This week only. Oh, I thought
Saturday one, ma'am.
Okay. Fine, no problem. Okay, anyway, we are starting system Verilog from March 1st. Whatever the leftover topics are there, we will discuss parallelly. Verilog and system Verilog. System Verilog we will run slowly, and mostly we will complete to Verilog by 10th, mostly by 10th. Okay, and leftover topics in digital logic design is static timing analysis, CMOS design. We have a special workshop on these topics. Maybe you already seen the brochure. If you didn't gone through the brochure, I will share you the brochure. Those workshop is taken by PD engineer. Okay, so we will you can join for first 3 sessions in that workshop, so that we will cover the overall static timing analysis concepts, CMOS design concepts, like power integrity and signal integrity concepts in that. Okay. So anyway, by March 15th, 20, by March 20, Verilog will be cleared. Okay. So meanwhile, we are starting the system Verilog also. So don't put any pending works. That's what I want to mention clearly. Okay. Once the system Verilog started, you will be getting system Verilog assignments also. Initially, system Verilog we will take slowly only. Okay. So once the system Verilog started from March 15th, we'll have regular proper assignments like that. Okay. That's what the next schedule for next few weeks. Everything clear? Everyone till here?
Is there any parallel tickle is going on?
No. As of now, we just kept on hold for tickle.
Okay. Yeah. Thank you.
Yeah. Okay. So next today topic, inferring of bad latches in Verilog. So what is mean by a bad latch in Verilog? Can you tell me, anyone? What is mean by a latch? Yeah, tell me.
Ma'am, I mean, bad latch is the one which causes extra delay.
Extra
Delay
Okay.
of the signal to transition, in my opinion.
Delay now. Okay.
Yes, ma'am.
How you are going to put that extra delay?
Extra delay. The delay can be added with the help of buffer.
Okay. In program, we are adding the buffer. So how you can add a buffer? Any other
No
answers?
idea.
It can cause a race around condition.
Okay. So how can we avoid that race around condition?
Uh, I mean, mainly we use flip-flop instead of latches.
Okay. Okay. That latch is different, and here whatever the latch is there, that will both are different. Okay. Let me explain. So in Verilog HDL, some bad latches will be occurred in some cases. Okay, not all cases. In very few cases, we get the latches. Those are unwanted. Unwanted means what? Suppose there is some combinational logic circuit. Multiplexer is there. So how the multiplexer will be look like? There will be few AND gates, AND gate 1, AND gate 2, AND gate 3, AND gate 4. And all these AND gates will be connected to one OR gate. So inputs are this side, outputs are this side. So this multiplexer we can implement in several ways, like behavioral modeling. We can use if else statements or case statements. Through if else and case statements we design, or else data flow modeling, or gate level modeling, like that. Okay. So suppose while you are designing this multiplexer, in few of the cases we will get some extra circuit, like a box. Suppose this is what we call as a latch. Okay, this extra box we can call as a latch, which is unwanted, because this is what our actual circuit. But if any unwanted box generated, if any unwanted circuit, it is a total mistake, right? Because that is not required. It adds extra functionality. Okay, if it add extra functionality, the total output will get wrong. Okay, so but in which cases these latches will be generated in a circuit, we need to understand that in which cases. So mostly in two cases the latches will be generated. Okay. First of all, whenever we take the code is incomplete, the code is incomplete. That means in two cases, one is a case statement. Whenever we use the case statement, we need to mention the default. Okay, or else whenever we use the if else statement, we need to mention the else statement. If you don't mention any default statement in any of these two cases, there will be a latch. Okay, so we definitely need to mention one any one of the case, like a default statement in a case X or case Z or parallel case, full case. Definitely in the next session I will tell you what is the difference between case X, case Z, parallel case and full case. Okay, so you will get the clarity. Okay, so how we write the case statement? Suppose multiplexer is there, a 4x1 multiplexer is there. So for 4x1 multiplexer, there will be two selection lines, S1, S0. So if S1, S0 is equal to 0, 0, so here I am putting as a selection line S. If S1, S0 are the selection lines, then what will be the output? So output equal to D of 1, suppose. And if selection line is a 0, 1, then what is the output? Output is getting assigned with a D of 2, and 1, 0 output is getting assigned with the D of 3, and 1, 1 case output is assigned with D of 4. Okay, so this is what simple case statement, end case. Okay, so here S is a 2 number of bit, S size is a 2 bit. 2 bit means 4 combinations. So for all 4 combinations, we have assigned some value. Okay, so even if you don't assign, suppose third case, I have not assigned any value. Okay, I just kept the code like this in my always block. In always block only we write the case statements, right? Always at the rate of posage clock, inside that begin, and inside the case S 0 0 0 1 1 0 cases. Okay, so if I didn't mention any of the case, whatever the possible combinations are there, in that possible scenarios, I have left with a few scenarios. Okay, in that case, when I am applying the inputs to the test bench, okay, suppose here I missed one case, okay, but in the test bench as a verification engineer, these things will be designed by design engineer. Okay, RTL will be designed by design engineer, verification will be done by verification engineer. The test scenarios will be generated by verification engineer. Okay, so as a verification engineer, we have generated few cases 1 0 1 1 0 1. Okay, so for 1 0 in the design we have some program, some functionality is there. So 0 will be assigned with a D of 3, and for 0 1 also there is some functionality. O will be assigned with some D of 2. Okay, but for 1 1 case we didn't mention any functionality in the design code. So what value would be assigned to the 1 1? Which value will be assigned to 1 1? Can anyone tell?
It's undetermined.
It's undetermined. Okay, so how undetermined can be shown in the output side? How we can identify that value?
It is shown as X.
Okay, it will be shown as X. Okay.
Yeah.
Okay, sometimes it will show as a X, or sometimes whatever the previous value is there, that value will be assigned in that stage. It goes to the memory state and that value will be assigned to here. Suppose previous is a 1 0. So next to as a 1 1, it may be get assigned with the previous value if there are any delay issues and all. Okay, mostly we will check, we will face those type of issues also, right? The same before value will be continued for next clock cycles also. Okay, these type of things will be happen. Okay, at the same time, so if it is storing the before value, if it goes to the memory state and if it is storing the before value, as a verification engineer in testing side we can observe that value. Okay, but as a design engineer, what type of circuit it will be generated in that place? Means a latch, unwanted latch will be generated in that place. Latch is nothing but it's a storage element, it's a 1-bit storage element, right? So in the same case here, that bad latch which is an unwanted, it is not necessary. Okay, but as we didn't use any default statement in the case, we left with without assigning some value to another last condition, it will automatically generate a latch. Okay, so if latch is generated in a combinational logic circuit, it's totally wrong, right? So overall functionality will be get affected with a bad latch. Okay, so for that purpose, in case statement we need to use default statement. Default O is equal to whatever the value, like a 2-bit binary 0 0 value you can assign, or any default value you can assign. Okay, so whenever other than these cases generated, then default value will get assigned to the case. So There is no chance of inferring any bad latches in the design. Okay, clear everyone? In the same way, if else also, suppose here we are writing the case. Suppose we are using the if else. So if s is equal to 0, 0, then what is the output? O is equal to D of 0. Else if s is equal to 0, 1, then what is the output? Else if s is equal to 1, 0, then what is the output? And finally, you must write else state. Else state is the default state for if else. If you don't write the else state, it definitely generates some latch because else state is not there. So if we generate any other case other than that which we mentioned in the if else, okay, so some data will be get assigned with that some other scenario. Okay, so to avoid that thing, we just use the else statement definitely in if else. Clear everyone till here? We do synthesis and I will show you how it is generating.
Ma'am, I have a doubt.
Yeah.
Will the default statement cause any hardware? I mean, is it synthesizable?
Yeah, default is synthesizable. It doesn't generate any hardware. Just it is a default case. Just we are putting as a condition. It doesn't
Okay.
generate any hardware. We are just putting some condition for default. That's it. Okay.
Yeah, okay, ma'am. Thank you.
So we'll write some program here. What programs are there before we'll see and we'll use them. Begin and okay. Okay, I'll take another program. Suppose this example. I'm changing the module name here. A module Verilog 1 current state comma flag input current state output reg flag some whatever you can try with the multiplexer also. Even I will show you with some multiplexer also. Okay, and always at the rate of current state case current state how many bits 2-bit size. So for the 2-bit size for 0 1 we assigned flag equal to 2. For third case flag equal to 0. Okay, but second case we didn't took anything here for second case. So what will be the circuit output? So you already know case will generate parallel multiplexer, if else will generate serial multiplexer. Both are multiplexers only, but case will generate parallel. The data will be taken parallelly. If else means series, one by one. One statement is executed, then next statement. Like that, it will generate a serial multiplexer. Okay, just run and check. Other than multiplexer, what additional circuit you can observe in the circuit. Go to analysis and synthesis, netlist viewer and RTL viewer. Still anyone facing any issue with the quarters prime? See here how it is generating. One additional latch has generated. Okay, but it should not generate any latch here. So how we can avoid this latch? Actually, it should generate only multiplexers for case 0, case 1, case 2, case 3, 4 case in 2-bit size. But instead of that, it generated a latch. Okay, so how we can avoid that? We'll modify in the program. So after 8th line, I am using default flag is equal to 0, or whatever the value you want to put, you can. Okay, so this is one style of adding some default statement. Now run and check.
Prasanti, this can only happen in combinational circuits.
It will be happen in sequential also.
Okay.
Because in sequential, if you don't write any default statement, it will generate same.
Okay.
See here, output is getting properly. There is no latch here. It is just a decoder and a multiplexer, and how the output is getting. Here, why we got a 3, 2 in the sense, if you observe here, for 3, we got the value, but for 2, we didn't use any value, any case. So these are the flag signals, one value, output values, and here flag 0 down to 1. Okay, so like this, a multiplexer will be generated. Suppose if I write any other program, like we already designed a lot of multiplexers, right? We'll say for one thing. I think Maxa we didn't return in case or if else. Even 7-segment display, you can try with those type of examples also. Okay. Here a priority encoder block is there, and also 7-segment display. Right side one 7-segment display is there. So not only putting default statement, you can also put like this flag equal to 0. After always current state begin a flag equal to 0. Like that also we can put. No need to use a default statement. Default is a predefined keyword it is, or else directly you can put here begin current state is equal to 0. Not current state, flag by default flag equal to 0, end case end. Okay, save and run. Here also it won't generate any latch. See, same circuit diagram. Okay, clear everyone till here?
Ma'am, if we follow all the conditions like 0, 1, 2, 3, then we don't need to use either flag or default value, right, in the design. So it won't
Yes.
generate any latch.
Yes, it won't generate any latch. Suppose here I'm just
Okay, ma'am.
removing
Thank
this
you.
default statement and I'm just putting 2 here. 2 condition is left, right? So for 2, flag equal to 1. So if you want to put default, you can put, or else I'm removing this default here. Save and run. Even if you write all the cases, you can put default also, not a problem.
Okay, ma'am.
So go through the analysis and synthesis block and RTL Weaver. See, this is how the block diagram will be represented, the decoder and the NOT gate. Okay. So here there are no latches, there are no bad latches inferred in the circuit. Okay. So clear everyone till here? Is it clear everyone? It's a multiplexer and also a NOT gate, because 0 0 0 1 1 0 1 1 we have both the complement value and also actual value, right? So it's a NOT gate operation. I think everyone got clarity. Next example for inferring of latches, I will look into else, if else statement. Here we have written for parity encoder. So what is a parity encoder? Priority encoder. Priority encoder means based on the priority signal. Like if any one of the input is high, suppose here 7 down to 0. 7 down to 0 means what? 8 number of inputs will be there, output will be 3 bit. So whatever the input is there, that will be decoded into the binary value. Okay, suppose here what is the encoder and decoder, how it will be work? Did you know everyone? Do you know how the encoder will work? Like if you give any input, suppose even keypad is there. We are working with the keypad, right? Okay, see here. Like a keypad is there. Whatever you are working in your laptop, you will be looking special characters. There is a 1 2 3 4 5 6 numbers, and special characters will be there, and also alphabetical values will be there. So how these values are converted into the binary value? We need to convert the ASCII value. So we are taking as a ASCII value of each character. Just a second. So for these special characters and also the alphabetical values, based on the ASCII value, the characters will be converted into the binary value. Okay, suppose priority in the sense we are typing as a high, H I. Okay, so which one will get a priority first? Obviously H is a first priority. So because we are clicking on H first. First we are typing H and then we are typing I. So obviously H will get a first priority, I will get a next priority. Okay, hi, any name. Okay, suppose hi name. Name in the sense N will get a third priority, A will get a fourth priority, M will get a fifth priority, and E will get the sixth priority. Okay, so based on that, which one we have clicked first, that will be highlighted based on the priority. Okay, so in the same way, here there are multiple number of inputs in 0, in 1, in 2, in 3, in 4, in 5, in 6, in 7. Okay, so in place of in 0, in 1, there is a, there is a B, there is a 1, 2, high, H, I, name, N, A, M. Okay, so suppose I'm clicking H, high, H first. First priority means this particular one will be highlighted, and that value will be converted into the binary value. So here 4 in 4 means it is converted into the binary value 4. Okay, like that I means suppose I value, whatever the ASCII value I is there, that will be converted into the binary value. Normally by decimal value means, you know, 1 what is the binary value, for 2 what is the binary value, for 3 what is the binary value, you already know. But for A, B, C, D, we don't know the binary values. It will be dependent on ASCII value, right? So I'm just telling in an example. Okay, like that I just clicked on 5 as an extra. So then 5 will get as a next priority, 101, fifth priority, and then 6. That value will be converted to 110. So this is what the priority encoder. First of all, encoder means whatever the physical data is there, that data will be converted into the binary value. Okay, that too, while we are converting into the binary value, so which one we are considering first and which one we are considering next. Okay, so if you see same this value in 0 to in 1, go through the encoder, priority encoder truth table. You will get like a steps. So 8x3 priority encoder. Okay, so what are the inputs? 0, 1, 2, 3, 4, 5, 6, 7. Total 8 number of values are there, 0 to 7. Okay, suppose I clicked on 0. Okay, so 0 will be getting high priority. So that data will be converted to binary as a 000. And next I just clicked on 4. Next second priority will get 4. So that 4 will be converted to 100. Okay, so based on the inputs we are writing the if else or case statement for priority encoder. Okay, so here we have written if else if statement. So we'll work with this and we'll check whether we get the latch or not. Everyone clear till here? So priority encoder, input code. Code is a output. Input a 7-bit, 8-bit size. Output 3-bit size. Okay. Suppose here I'm removing this statement. Else if statement I am removing, and also else statement also I am removing. Okay. Now we'll check what is the output. Go to Netlist Viewer and check RTL Viewer. So see how many multiplexes are generated. And also if you see here, latch 1, latch 2, latch 3. 3 number of latches are generated for these type of, for these outputs. Okay. So code 0, code 1, code 2, code 0, code 1, code 2. Okay, here. Output of code 0, 1 multiplexer, code 1, code 2, code 3, like that we got the outputs. Okay, whatever the circuit diagram it is, but at the final stage we got the latches. Okay, latch 1, latch 2, latch 3. But these latches are unwanted latches. We need not to get any latches like this because it's a combinational logic circuit. In combinational we don't have any storage element. Even if we have the storage element, it's unnecessary. It is like a functionality will get wrong if it is there. Okay, even in sequential logic circuit also, if any latch is generated, it's unwanted only because it will get the functionality wise it's wrong. Okay, so how we can avoid this bad latch? Now write the else code here. Else code equal to some value, not only x, any value you can mention. Okay, so even if you don't use the 7th case or 6th case or 5th case, whatever, even if you don't use, that's not a problem, but else statement must be there. That's the default case. So if you write else, we won't get any latches. So go to Autrial Weaver and see. We didn't got any latches, just multiplexers. Because these are all if else condition. If else means all serial multiplexers will be generated. If you see before case output, how the multiplexers are generated one by one, top to down. Okay, like this, no one connected, like one output is getting to another input, another input is connected to another next multiplexer. Like that, we didn't got like a series. So that's why we call if else means it generate a serial multiplexers. Case means it generate the parallel multiplexers. Okay, everyone clear till here? Any doubts? Like that, try with the 7-segment display. So how the 7-segment display will be worked? Do you know the functionality 7-segment display? So this is what we have, the 7-segment display. If you connect with any FPGA, the LCD board, okay, the how the glow, like light, which light will be highlighted in which based on the input value. Okay, suppose you are giving input value as a all zeros. All zeros means what? How it should be glow. This 0 will glow, and here, here, and here, here, and here. Like that, we will get the 0. So this one will not activate. Okay, so here we will write like this: A, B, C, D, E, F, G. And truth table you need to write for 7-segment display. What is the truth table? Based on the input signals, input or the BCD signals. BCD means from 0 to all ones, or else till how many numbers it will be printed, till 9, right? 7-segment display means 0 to 9 it will print. So 0 to 9 means what? 1 0 0 1. So for 0 you need to write the output. What is the output here for 7-segment display? These display values will be the output. Okay, so what are, how many outputs are there? A, B, C, D, E, F, G. These many outputs will be there: A, B, C, D, E, F, G. Okay, so if you see here output, 40 means 7 segment is equal to all zeros, so last one only 1. Why all zeros? It will be starting from here like this: A, B, C, D, E, F, G. Okay, only G is high because G we don't have light here. It doesn't glow. If you want to write as an active low, then you can highlight as a 1 for A, B, C, D, E, F. If you want to write an active high, I mean active low means you need to highlight with the zeros. If you want to write an active high, then you need to highlight with the ones. Then G will be the 0. Okay. Next, suppose you want to 6, suppose 6 or 7. Suppose 7 is there. 7 means which LEDs will glow here. 1 here, here. 7 means like this, right? That means A, B, C will be high, remaining all are 0. Or else A, B, C will 0, remaining all are low. Okay, see here. A, B, C or 0, remaining all are high. Okay, like that you want to on 8. 8 means what? 8 means like this. All will glow. So all will go to zeros like this. 8. Like that 9. 9 means these only. ED will not glow. So near ED we will put as a 0, 0. For 9. Oh, 9 means like this, right? Like this. That means this light will not glow. So there we put 1, remaining all are zeros. Okay. So try this example. Okay, 7 segment display and check the output. Okay. So you can check with the latch also. We'll do synthesis and we'll check. You need to practice. There are a lot of examples, but I don't know whether you are practicing or not. So here I am removing the default statement, suppose, and also I am removing, okay, no need to remove, already BCD is a 16-bit size, so obviously we'll get the latch here. Verilog 1, okay, write the module name as a Verilog 1. Whatever you are saving with the file, both file name and module name must be same. So RTL Weaver. See, we got the latches like this, but we need not to get these latches. Okay, so for that purpose we need to use the default statement. Okay, and the thing, if you observe, before in if else all are serially connected, one after another, one after another, but here in case statement all are parallelly connected, all multiplexes. Okay, so I am writing the default statement here. So in this case we can avoid the latch. That means what? Whatever remaining, suppose here till 9 only we have kept in the loop. Okay, then what about 10, 11, 12, 13, 14, 15? For all these statements, if we do the verification, some other value or x value will be generated. So that value would be stored in the latch, because we are not writing any output for those conditions, right? So that's why for those conditions it will be generating the latch. Okay, so to avoid that latch we are putting the default. That means even if any value is generated between that in the test case, this default value will be assigned to the output. Okay, so that's what we are mentioning here. See, latches are avoided, and also how the signals, if you see here, what are signals are high, low, check properly. Okay, everyone clear till here regarding the latches concept? Any doubts? There are some more examples. ALU for arithmetic and logical unit. What is meant by arithmetic and logical unit? Which performs the arithmetic operations and logical operations like addition, subtraction, multiplication, division, logical and or XOR, not, whatever. Just try the example here. That's it for latches. Clear, everyone? Any doubts? Hello,
No doubt, ma'am.
everyone?
Clear, Shanti.
Clear,
Okay.
Prashant.
Next, generate block. So what is mean by generate block? Normally, for loop is not synthesizable, right? Even if you write a for loop in design, suppose we will take one example of for loop where we have written a for loop example. Mhm. Okay, we didn't written anywhere. Okay, but I'm taking here in the same example. In always block, I'm removing the case. For int I is equal to 0, I is less than 7, I plus plus, output is equal to, what is the output of segment? Segment is equal to BCD value. Okay, whatever BCD is the input, right? So BCD value, I'm just putting like this. Okay, so how we'll see what will be the output. So what are the errors it generated? Syntax error, sixth line, expected equal to check for fix. Okay, it is expecting non-blocking assignment. Okay, we put non-blocking assignment and we'll check. Check immediate before.
In for loop, it is expecting less than I less than or equal 7.
No, in for loop we cannot use like that. For loop is correct only, but here for loop is not synthesizable. That's why it is giving the error. But we'll check once again in EDA to observe proper error here. It is considering as a test bench. Mostly in simulation tools, it doesn't reflect, but in synthesis tools like this, it will reflect here. It is not giving for loop. It is not mentioning for loop, but indirectly it is mentioning the error here. And also, suppose if we see, we cannot put like this because both are equal to, less than or equal to. It is a syntax error. We should not get the syntax errors. We should get the functionality errors. see. It's not syntax error. Check for and fix any syntax errors immediately. So I'm just removing this.
After for colon is there, right?
After for
Colon is there, right? Colon, can you remove the colon?
okay,
After for end of the line. End of the line.
okay.
No, not inside, end of the line.
Near I expecting equal to check for and fix syntax error. Suppose same, we will use a generate block and we will check. Okay, because for loop is not synthesizable. Suppose if we
No,
consider
Prashanti, here first initialize I equal to 0, then it will take first.
I is equal to 0 now. Okay, okay.
Yeah,
Yeah, before also I kept I equal to 0 only. I just
yes.
changed. But still we will get the error for loops in design. Yes. Near text I, it is getting some error. We will fix this thing with by using the generate block. Okay, suppose if we think for loop is not synthesizable at this point of time. So I will explain you what is meant by generate block. So generate statements in Verilog allow code to be dynamically generated before simulation or synthesis begins. This feature is extremely useful for creating parameterized module description. For example, a ripple carry adder can be described generically for any value of n. So for you, by using the generate block, we can use in any modules or user-defined primitives like UDP examples or gates, continuous assignments, behavioral blocks, anywhere we can use. But we need to use the special variables for generate block. One is a genvar. Genvar means what? First of all, here I is not synthesizable. Here we are getting the error like I near text I expected equal to check for the fix. Okay, normally here I is not allocating the value of 0 or 7. Okay, so first of all that I
Actually,
we need
sorry for
to
the
declare
interruption.
value. Yeah,
Actually, integer keyword is not, data type is not taking in the design actually.
okay.
Previously also I checked, if we give another, I asked, right, another data type is there for accessing the integer in the design.
Okay. Yeah, in
Mm.
for loop we cannot use that. That's what I'm telling here.
Yeah. Yes,
Whatever
yes.
we
That
use,
is a problem.
okay. Even if we use integer, also will not take. It will not
No, no,
take.
no. Not the integer means that the data type itself is not taking. Like integer, it's not taking in the design. In test bench, it is allowing.
Yeah, that's what I'm explaining now.
Yeah, yeah.
So here I we need to declare as a genvar, not integer or int in for loop. Okay, so that's what we are getting the error here. Okay, so I must be declared as a genvar keyword. If you see here, genvar, a keyword to declare variables specifically for use in generate blocks. These variables only exist during the evaluation of the generate block. Okay, so a genvar can only be assigned values within a generate loop. So these are the examples. If you see one of the example, so whatever for loop we are using here, for p equal to 0, p is less than and p equal to p plus 1. Okay, internally there is something, but this p we need to declare as a genvar instead of using int or integer in like a Verilog HDL. We need to declare it as a genvar. Then only it will do the synthesis. That too this for loop we need to write within a generate block, generate and generate. Okay, then only it will do the synthesis. Okay, so we'll see that. I'm just removing this integer here, and I'm writing generator genvar I. Generate and generate. So within the always block, no need of always block anything, just we need to write the generate and generate within that for loop. It will generate multiple number of instances directly. So remove these things and module. Okay, now we do the simulation synthesis. Here text expecting for loop again for I equal to 0, I is equal to I plus 1. What is the error? Near segment expecting begin end. Okay. Eighth line. Okay. Because it's a combinational logic circuit. Note or this block requires a name. The line. We'll see with this example once. Okay, here XOR is generating multiples of P. Okay, let me explain this example. First, we'll see the netlist. Okay, XORs are generating. Okay. In the same way, if I try Actually, whatever the I have used here, I didn't written any functionality here. Suppose BCD of I assigning to 7-segment display, then we'll see whether it will work or not. Actually, I didn't took any proper functionality for this. I just written some piece of code. Seventh line requires a block level name. Okay, fine. We'll see with this example only. Actually, here in structural modeling, if you see, like if you want to write a multiplexer, hierarchical multiplexer, how we can do? First, we will take a multiplexer program and we'll make the copies. Suppose the 16:1 multiplexer using 4:1. First, we write the 4:1 multiplexer main program, and we'll take the multiple copies, like 5 copies of multiplexer, and we will write in a structural modeling like this. Suppose here it is a 16:1 multiplexer. So first we took a 4:1 multiplexer and we written the copies here. Okay. But without writing it like this, we can write using a generate block, even ripple carry adder also. Without taking the multiple copies like that, simply in a single line, we can generate by using the generate block. Okay, so first we'll see the example for XOR, then we'll write for the ripple carry adder. Okay, so if you see here, what is the main intention of this program? It's a module XOR bitwise operator. So you already know what is a bitwise operation based on the input. Suppose what is the size of A and B here? N is equal to 16, parameter. Parameter means where we can declare a constant value. So parameter n equal to 16. That means wherever we use this n in the program, that n is allocated with a 16 value. Okay. So input n minus 1 down to 0. So 15 minus 1, 16 minus 1, 15. So 15 down to 0. So A is equal to 16-bit data, B equal to 16-bit data. So what is the program intention? XOR bitwise. You already know the bitwise operation, right? What is the difference between bitwise reduction operator and logical operator? You already know. So this 16-bit value will be assigned to A, and B will be assigned with a 16-bit. So normally, if you want to write the program for this, how we can write every bit to bit, we need to do the XOR operation. So A of 0, B of 0, XOR. XOR of A of 1, B of 1, XOR of A of 2, B of 2, XOR of A of 3, B of 3. Like that, every bit to bit, we need to do the XOR operation. Okay. But without doing that, by using a simple for loop, how we can generate the hierarchy of XOR gates? If you see here, first we are creating the for loop for p equal to 0, p is less than n, p equal to p plus 1. So p should be declared with a genvar. Normally in for loop we use int p or integer p, but in Verilog in design, for loop is not synthesizable. Okay, so that purpose we need to use, we need to declare this p as a genvar. Okay, genvar p, and generator. Within the generator and generate only, we need to write a main functionality. Okay, so for p equal to 0 to n, begin. This is just name of begin. XOR, we are doing the XOR operation. XOR xg is the name. FP, like structural modeling, we will connect to what are the input, what are the outputs, right? Same here also we are connecting. F is the output, A is the input, B is the input. Okay, so F of P. F of P means what? P is the n bit, n value. N is a 16. So A, B will be 15-bit size. Total 15 down to 0, 16-bit size. And that too, P will be having the iterations from 0 to less than n. That means 0 to 15. So this XOR block will be iterated for 16 number of times. That means F of 0 is the output, A of 0 is the input, B of 0 is the input. Again, next loop, F of 1, output to A of 1, B of 1. Next F of 2, A of 1, A of 2, B of 2. f of 3, a of 3, b of 3, f of 4, a of 4, b of 4. Like that, every bit to bit it is doing the XOR operation and assigning the output to f of p. Suppose I am taking here as a 4-bit, suppose a is a 4-bit size and also b is a 4-bit size. Okay. So in first operation, it is considering b of 0, p of 0. So 0, 1. 0, 1 means what is the output? Output is 1. Next case, a of 2, b of 2. Then output is 1. And next case, a of 3, b of 3. Output is 1. Next, a of 4, b of 4. Output is 1. So this value is getting assigned to p. But do we writing all number of times, like every bit to bit? Normal case we need to do the operation for every bit to bit, but here we are not doing for every bit to bit, just we are creating one XOR gate and passing the value p to the f, a and b. Okay, so that thing will be happen through for loop and through generate block. For loop is synthesizable whenever we use generate block only. Okay, so if you see the synthesized output here, after doing synthesis, RTL Weaver, go to RTL Weaver and check here how many XOR gates are generated. XOR 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 0 to 15 number of XOR gates are generated by using a single line XOR program using a for loop. Okay. If you do simulation, you will get this simulation result. Any doubts still here? Everyone? So see here, same XOR program by using the generator. So genvar p generate block and XOR. So in this test bench, we are passing the value a hexadecimal 4 A's. 4 A's means a value is a 1010. So 10 1010. So b value is a 00FF. 00FF means all 4040. So 4 ones are 4 ones. So what will be the output of XOR? And after 10 time units, X value is 0F 0F. Y value is 3333. Okay. So run and check the output here. This is how we can generate by using a single statement. What is the error? Syntax error test bench 11. Generator, begin and end generator.
After begin, use the colon.
After begin colon
Yes.
here.
Yes, yes. In the, I mean, when you executed in the quarter sprint, it was there.
Okay, colon. I thought semicolon. Okay, so X value all is and Y value 0011 and what is the output? Just check with that and second case also. Okay,
What that
clear?
indicates that colon XRLP? Can you explain that line?
It is just indicating this XOR name inside the
Okay.
functionality. Yeah,
Okay.
XOR LP is just a name of that synthesized diagram. So if you see all are XOR LP of 1, XOR LP of 2, XOR LP. So it indicates the name here, all XOR gates.
Okay.
Like that, I have given one problem statement here. Design a n-bit ripple carry adder. So full adder is given here, but how we can synthesize by using the generate block. So how we can write the full adder or ripple carry adder using generate block. You need to write that program. Before that, I will show you another example also for shift register. Basically for shift register, how we have written before, we took the structural modeling and written one first D flip flop and then took the multiple copies of that. Okay, so here also first take the D flip flop and by using the D flip flop here I am taking a generator loop, genware creating with the n generate for loop and equal to 1 to less than depth and by using the D flip-flop creating the multiple number of flip-flops here. Okay, so just I'm doing the synthesis and try from your side also how it is generating the output. Next UDP concept we'll discuss in the next session. What is that? Very long. Doc requires a name. Same before, however, we written for loop like this. Inside a D flip-flop for each register. So simply by using for loop also we can generate the multiple copies of shift register. Everyone understood till here? Any doubts?
No, ma'am.
No? Okay. So what is the rule here? Segment equal to BCD of P. This functionality itself is found. We just need to give like this hierarchy. So okay, functionality itself for 7-segment display, how we can take in here. Okay, it totally different. We'll see in the next exam, next session.
Yes.
So I already told the schedule, right? So you can plan accordingly. Yeah. Okay.
Yeah. Thank you.
Yeah. Okay. Thank you all.